Hi, I'm Jonathan Selinger, and I'd like to tell you about violation of Ericksen inequalities in lyotropic chromonic liquid crystals. This is work with my graduate student, Cheng Long. Let's begin with the elastic theory for liquid crystals. Okay, you know that the Osane-Frank free energy tells us the free energy cost of gradients in the director field. It is conventionally written like this, with terms associated with splay, twist, and bend, and this additional saddle splay term. A few years ago, I suggested a reformulated version of the same free energy density, which looks like this, expressed in terms of splay, twist, bend, and this fourth elastic mode called delta, illustrated in this picture. That was my talk at the APS meeting in 2019, and it's described in this article. Okay, so the point is that these two expressions for the Osane-Frank free energy are mathematically equivalent to each other. Now, whenever you have an elastic free energy, someone is going to derive conditions so that the free energy will be positive definite. Okay, and Ericksen did that for liquid crystals in 1966. He derived these four inequalities, and especially notice the inequality that K22 has to be greater than K24. It was a hard job to derive these four inequalities when he was working with the conventional expression for the elastic free energy. But in terms of my reformulated expression, it's actually kind of trivial. Those four inequalities are just saying that the four coefficients of these elastic modes squared all have to be positive. All right, so this is great for most liquid crystals, but there's a problem when it comes to lyotropic chromonic liquid crystals. Okay. So there's been experiments by the groups at Georgia Tech and the University of Pennsylvania, which put lyotropic chromonic liquid crystals into a cylindrical capillary. So the director field could be uniform, but it isn't. Instead, the equilibrium director field has some spontaneous double twist going from the center to the edge of the cylinder. So those experimental groups analyzed the data and extracted the parameters K22 and K24, and they found that K22 is less than K24, which violates one of the Ericksen inequalities. Okay, so what's going on here, right? How can we understand this result? And are there actually any constraints on K22? Like, could K22 actually be negative? All right, well, negative, no. Okay, let's see why not. Suppose you have a cholesteric phase, as shown here, with this helical director field. If we put that into the free energy, we get this average free energy density, a half K22 times Q squared. If K22 were negative, then the system would minimize its free energy by sending Q to plus or minus infinity, and the free energy would go to negative infinity, which would be thermodynamically unstable. Therefore, we conclude that we can never have K22 negative. Never in this context means unless there are some higher order terms to stabilize the free energy. But that's not the subject of my talk today. Instead, my talk is about the case of K22 greater than 0, but less than K24. So in this intermediate regime between 0 and K24, what happens in that regime? To understand that regime, let's consider a double twist structure as illustrated here, okay, inside a cylinder with radius R max and totally free boundaries. The liquid crystal can do whatever it wants at the boundaries. Okay, so we put in this odds for the double twist structure, where the director is vertical right at the center, and then it tilts over as a function of the radial coordinate. So the tilt is equal to a parameter alpha times the radial coordinate. If we put that into the free energy and average over the volume of the cylinder, we get an average free energy density, which can be expanded as a power series in terms of this coefficient alpha. Okay? It has a term proportional to alpha squared, a term of alpha fourth, etc. Okay? The quadratic term here has a coefficient of K22 minus K24. This looks a lot like what you'd expect in the theory of a second order phase transition, right? It looks like when K22 is greater than K24, the minimum free energy has alpha equals 0. That is, it's a uniform configuration. And when K22 is less than K24, then the optimum value of alpha shifts away from 0 to be positive or negative to give a right or left-handed double twist. So this configuration is not uniform, but it is thermodynamically stable. The free energy is this finite negative number. It doesn't go to negative infinity. We might interpret this result as saying that the liquid crystal is stabilized by compatibility conditions. That is to say, if it could have twist and nothing else, then it would be thermodynamically unstable. But it can't have just twist. Whenever it has twist, it needs to also have some bend and some delta mode. And those things cost positive free energy, which gives the thermodynamic stability. Okay. You might ask, is this linear assumption, is that valid, right? So to check that, we've made a numerical solution of the Euler-Lagrange equation as shown here. And we can see, yes, right, if K22 is slightly less than K24, as in this yellow line, that indeed the tilt angle theta is linearly proportional to rho. So that's no problem. Okay. You might ask, can the double twist structure just keep on repeating, right? If one double twist domain is good, maybe two are better, maybe four are even better, and so forth. So if we wanted to make a repeating structure, it could look like this if we had all double twist of the same handedness. Or it could look like this if we have domains of alternating handedness. In either case, the repeating structure requires disclinations in the director field, which cost free energy. So it's only favorable if K22 is a lot less than K24, so that the difference exceeds the disclination core energy. This does not seem to be the case in the experiments. The experiments show one double twist regime and not more. Okay, so the experimental behavior involves twist. Okay, so that shows what happens if the Ericksen inequality on K22 is violated. There could, in principle, be analogous behavior for splay or for the delta mode. Right? So if K11 is in this regime between 0 and K24, you could get some spontaneous splay like this. If K24 is negative, you could get some spontaneous delta mode, as in this picture. So these are theoretical possibilities which haven't been studied in experiments so far. So to put the results together, we can make a diagram showing regimes of the elastic constants. Okay, so here's a diagram in terms of K24 and the difference, K22 minus K24. We can see there's this Ericksen regime where both of these quantities are positive and the optimum local state is uniform. Then there's the twist intermediate regime, where we have lyotropic chromonic liquid crystals. The optimum local state has double twist. In principle, there could be this delta intermediate regime with the optimum delta deformation, and then a forbidden regime, which is thermodynamically unstable. Here's the same diagram plotted in terms of K24 and K22. We also have analogous diagrams in terms of K24 and K11. So, to summarize the conclusions of this study, first, as a theoretical point, we have these distinct regimes of elastic constants in nematic liquid crystals. There's a regime where the Ericksen inequalities are satisfied. The ground state has a uniform director. There's the intermediate regime where the ground state has double twist, stabilized by the compatibility conditions. And the forbidden regime, which is thermodynamically unstable unless there are higher order terms. Okay, and conclusions for experiments. We'd expect then lyotropic chromonic liquid crystals should be very sensitive to the geometry of their container. That determines what kinds of twisted structures can form. We expect that double twist should be preferred over uniform, which is in turn preferred over single twist. And we expect that lyotropic chromatic liquid crystals should be especially compatible with impurities such as dust or colloidal particles, which would make domain walls without disclinations and hence make more regions of double twist. So those are the main conclusions. I thank the NSF for support, and thanks to you for watching.